All right, good morning, everybody. If you're watching this in the morning time, it's October 30th, and this is going to be Explore number 3. So let's go ahead and jump right to it. Monday, October 30th, and leave a little bit of room for ourselves as always. Our essential question, how are valence electrons? How are valence electrons represented? Let's see here. Represented within a Lewis structure. Okay, let's go ahead and just start. Try to have a good practice here of saying what you already know. What I know. Okay, and I'd like you to pause for just about a minute. Hit pause on this video and just write down what you know. Perhaps you've taken this class before, you've been exposed to the material that way. You all have been exposed to Lewis dot structures in middle school. So kind of dig back what you recall. All right. Hopefully by the end of this set of notes, when we write our summary paragraph, you'll be able to write a little bit more about Lewis dot structures. But in effect, you should have said that it was a shorthand method for representing the number of electrons in the valence shell of an atom. That's kind of it in a gist. So let's take a look at our notes over here on the left, our text. We've got Lewis structures. They're going to talk about electron configuration, which we've already known and talked about. You can see a nice little table here showing the various Lewis dot structures for some of the group numbers, 1 to 13 through 18. Got some videos there talking about the reactivity of atoms, covalent bonding, valence electrons, and electron configuration. Remember, we're trying to set you guys up to understand bonding, right? That's where this is all going. And videos on Lewis dot structures, a lot of good resources down here. So make sure you look at those, okay? So let's come back up to the top here, and we'll go ahead and say Roman numeral 1. Lewis structures. And if you've already read this, and again, I encourage you to pause and read this text first. That way, when you come back to take your notes, this will make more sense. In most elements, electrons in the outermost energy level of an atom are valence electrons. That's good. Okay. In most elements, electrons in the outermost energy level of an atom are the valence electrons. Okay, they are the valence electrons. Okay, what does that mean? AKA, they reside in the highest occupied energy levels. Okay. they occupy the highest energy level. Right? And I guess if we're to draw that, you could say that if you had something like an atom, and it had a 1s, it had a 2s, and it had a 2p, versus a atom. There's your 1s, there's your 2s, there's your 2p, and then you have this 3p. We could say that this 3p and we could say that this was a 2p. So the 3p is going to obviously be higher in energy, okay? And many properties of an element are related to these valence electrons. You can see I'm kind of coming back over to this section here, and we're just highlighting this idea, right? And these properties are things like whether they're going to form ionic or covalent bonds, right? So that's kind of an important piece to understand here. So let's just put that as letter B, okay? Letter B. Many properties i.e., will they form an ionic or covalent bond, are determined by valence electrons. Okay, so those outer electrons are pretty important. Going to paragraph number 2, the total number of electrons at the highest energy level dictates the number of valence electrons. That's kind of it right there. Okay, so let's write this down here. Letter C, the total number of electrons in the highest energy level dictates the number of valence electrons. Okay. All right, so let's get down to Lewis structures, because he, as you can see in paragraph number 3 here in 1916, figured out an easy way to represent these things. Okay, so letter D here. Lewis structures. An easy method for representing atoms and their valence electrons. Okay. So in general here, as you can see in red here, you simply have the chemical symbol surrounded by dots. Lewis structures follow trends in the periodic table. And here's the trends moving across a period. A dot is added for each additional electron in an atom of the element. The number and pattern of dots is the same moving down a group. So let's really quickly just draw out something here. And we'll just kind of say that this is our periodic table. So for example, if we were to draw out a periodic table, just see if I can kind of do this here. 1, 2, 3. One, two, three, 4, 5, 6, and we have one more column up here. Okay, so this would be like your 1A. Let's see. We got our 2A. We have our 3A, 4A, 5A. We have the 3, 4, 5, 6, 7. Oh, I think I kind of messed this up just a little bit. This is the way it should be here. We have 6A, 7A, and 8A. And so as you go to the right, increase by one electron. Okay, we're talking about for the valence. And as you go down these groups, the valence stays the same. Valence number remains the same. So if we were to go ahead and draw something like, hey, Chris, if you can go and just close that door there. Great. Let's just see here. Erase that guy. So if we were to go ahead and draw something like hydrogen, examples, let's just get right to our examples. We could say that hydrogen is in the 1A group. It's the number 1. It has only one, that's its atomic number. We could represent it as hydrogen, and we could say it has 1 dot. And the reason why it has 1 dot is because it has a sphere, remember, and in that 1s level, it has 1 electron. This is our 1s, right? So 1s1, I guess, is what we could write that down. So there's your hydrogen. If we were to go ahead and do something like, say, helium, and helium has 2, it's in the 2A. When you take a look at helium, it actually is lumped with this one over here, over in the second group. We go ahead and say that helium has a valence of 2, but we draw it still like this because there's an upspin and a downspin. They're occupying the same energy level. So we have 1s2 for helium. And so we draw our sphere, and what we're doing is we're showing that inside that 1s shell, you have 2 electrons. Okay, if I were to go all the way to the other end to the 8A group, then it would look something like perhaps this. I'm just going to take neon, and if you look on the periodic table, it's the 8A group, and neon has actually 10 of these guys. So I'd write neon. It has a full valence, and I go 1, 2, 3, 4. Then you can start to do the backfilling, 5, 6, 7, and 8. And if you draw that out, it would look something like this. Neon, it has a 1s shell, it has a 2s shell, and then it has 1, 2, 3, 4, 5, 6, 7. So let's try this in here. We got 1, 2. We've got 3, 4, 5, 6, 7, 8, 9, and 10. So which ones are we counting here? We're counting the 2 level. So in the 2 level, you count the highest energy level, which is the 2 orbit, and you got S and P. So you count the S and P. You got 1, 2, 3, 4, 5, 6, 7, and 8. And those are going to be here. These are all your 8. 1, 2, 3, 4, 5, 6, 7, and 8. All right. Moving on, then, the last thing that they talk about when you're doing these is that you can represent Lewis structures as chemical bonds as well. So, not just atoms with their electrons. And what they're referring to is that you can have, for example, H2O. Where you have hydrogen and hydrogen. You can have Lewis dot structures use lines for covalent bonds, and you use the dots to represent the lone pairs of electrons. These are ones that are not bonded. And we'll talk about that a little bit in class, okay? But this is kind of just a shorthand way of describing molecular bonding using Lewis dot structures. All right, hopefully that helps. Please write yourself a summary paragraph now.